We're going to graph and analyze the rational function in example 1D of notes 4.2 day 1. Our rational function is partially factored, but we're going to have to factor it completely in order to do our analysis. So the difference of squares in the numerator we're going to factor as x plus 1 times x minus 1, which is going to give us x plus 1 squared times x minus 1. And we also have a difference of squares in the denominator, which is going to factor as x plus 2 times x minus 2. Let's first find x-intercepts. Okay, x-intercepts occur when the numerator is equal to 0, but the denominator is not equal to 0. Here we're going to have x-intercepts at negative 1, 0 from the factor x plus 1. That's going to have even multiplicity, and we're going to have an x-intercept at 1, 0 with odd multiplicity. And I'll go ahead and record these in our table. Negative 1, 0, and 1, 0. And this one has even multiplicity, and the x-intercept at 1, 0 has odd multiplicity. Next, we'll find the y-intercept. The y-intercept of any function is found by evaluating f of 0. So here, f of 0 is going to be, it's easier, I guess a little easier to evaluate from the original form of the function. So we're going to have 1 times negative 1 over 0, which is undefined. So we have no y-intercept because that makes 0 makes the denominator 0. Let's find vertical asymptote. Vertical asymptotes are found by finding values that make the denominator equal to 0, but the numerator not equal to 0, or if it makes both denominator and numerator 0, then it has to be a factor that we cannot cancel out from the denominator. Otherwise, it becomes a whole. In this case, we're going to have a vertical asymptote from that factor of x at x equals 0 with odd multiplicity. So x equals 0 with odd multiplicity. And we're going to have vertical asymptotes at x equals negative 2 and x equals 2 from these other two factors, all with odd multiplicity. So x equals plus or minus 2, I'll put here to save a little space. Wholes occur when we have common factors in the numerator and the denominator. In this case, we have no common factors between numerator between the numerator, I'll write it all out, numerator and denominator. So we have no wholes, none. So no wholes, we don't need to worry about that in this case. Now we'll talk about the infinite asymptotes, or the n behavior. So infinite asymptotes, to determine what type we have, we're going to look at the degree of the numerator and the degree of the denominator. This is in factored form, so we need to add the exponents. So the degree of the numerator is actually 1 plus 2, which is 3. And the degree of the denominator is 1 plus 2, which is 3. So the degree of the numerator equals the degree of the denominator. That tells us that we have a horizontal asymptote at the ratio of the leading coefficients. In this case, that's 1 over 1, which is 1. So we have a horizontal asymptote with the equation y equals 1. We will not have a slant asymptote. We cannot have both a slant and horizontal asymptote in our same graph. And last, we want to know, does our graph intersect the horizontal asymptote? To determine that, we're going to set our equation, our original equation, equal to the horizontal asymptote. So I'm going to do that here. I'm going to set that equal to 1. Multiply both sides of the equation by x times x squared minus 4. So we're going to have x plus 1 times x squared minus 1 is equal to x times x squared minus 4. And if we expand this, we're going to get x cubed plus x squared minus x minus 1 is equal to x cubed minus 4x. And combining like terms and putting everything on one side of the equation is going to give us x squared plus 3x minus 1 equals 0. The x cubed terms will subtract off. And this is a quadratic function that we cannot factor, so let's use the quadratic formula to see where the points of intersection occur. Or you could also complete the square. If we use quadratic formula, we have negative 3 plus or minus the square root of 3 squared minus 4 times 1 times negative 1 all over 2, which gives us negative 3 plus or minus the square root of 9 plus 4, which is 13 all over 2. So we actually have 2 points of intersection. The x values are negative 3 plus or minus the square root of 13 over 2. And the y value comes from this horizontal asymptote because we're intersecting that horizontal asymptote, which is at 1. And if you punch this into your calculator, you can get decimal approximations, which turn out to be about negative 3.3, 1, or 0.303, 1. All right, we are ready to make our graph. Let's go ahead and put on our x-intercepts. So we've got one at negative 1, 0, that has even multiplicity, and one at 1, 0 with odd multiplicity. I'll put the vertical asymptotes on at negative 2, 0, and 2. So x equals negative 2. And these all have odd multiplicity. So x equals negative 2, x equals 0. X equals 0, and that's odd. And x equals 2. X equals 2, and that's odd. And then I will put in the horizontal asymptote at y equals 1. Y equals 1. And then I'm going to put on those points of intersections that we found between the horizontal asymptote and our graph. We might as well use those. So we have a point at negative 3.31 and a point at 0.3, so just about here, 1. All right, and now we're going to try to put all these pieces together to sketch our graph. So here we go. Let's start in this interval right here. I know this is an x-intercept with even multiplicity. That means my graph needs to bounce off the x-axis here. If we're bouncing upwards, I would cross my horizontal asymptote, but there are no points of intersection in this interval between x's negative 2 and 0, which means that my graph needs to be going downwards in this interval. You know what, I think I might switch to the blue pen. I think that might be a little easier to see. Yeah, okay, so it's going to be going down on both in that little interval. Once we go across x equals 0, this vertical asymptote, what's going to happen? This is an odd vertical asymptote, which means the graph is going to cross the x-axis and has to be shooting upward here. The graph will be coming down. It's got to go through this point, 0.31, and then it has to cross through this x-intercept with odd multiplicity, and then it's going to continue on and approach this vertical asymptote at x equals 2. As we cross the vertical asymptote at x equals 2, going to numbers a little greater than 2, we have a vertical asymptote with odd multiplicity, which means our graph is going to once again cross the x-axis, or the ends here will shoot in opposite direction. So it's shooting down here, which means it's going to be shooting upward here to positive infinity. And then it's going to be coming down. It cannot cross the horizontal asymptote. We found those points of intersection, so our graph is going to approach the line y equals 1 as x goes to positive infinity. We have one more region to work with, so let's go to the left of negative 2. This was also an odd vertical asymptote, which means if the graph was shooting down to the right of x equals negative 2, it's going to be shooting up to the left of the vertical asymptote at x equals negative 2. And now it's going to pass through this point of intersection between our graph and the line y equals 1. And now we have to figure out what's going to happen. So it's going to cross through here, but we don't have any more x-intercepts, so it cannot cross through the x-axis. So it's going to have to turn around and start to approach the horizontal asymptote at y equals 1 as x goes to negative infinity.